Hello everyone. In this lesson, we will learn Low-Frequency Electronic Circuit Chapter 3, Field Effect 2. 3.2 Junction FET. Nodal FET is a MOS-type FET, another kind of field effect 2 with different structure. Nodal field effect 2 and its working principle. It uses the electric field effect in semiconductors, variation of VGS by grid source voltage, changing the width of barrier layer, thereby change the width of conductive channel, control leak source current ID. So junction FET and MOS FET work similarly. They all use the electric field effect to control the current. The difference is that the formation principle of conductive channel is different. Let's look at the junction FET, structure and its circuit symbol. Nodal FET is divided to N-channel junction FET and P-channel junction FET. On the left is an N-channel junction FET. It is structured on an N-type material. Two P-shaped regions stopped on the left and right sides. The P-type region on the left and the right side is the grid. So the upper and the lower ends of the N-type region, defined as drain and source. N-channel junction FET symbols as shown in the PowerPoint. Connection from grid to channel. It is indicated by an arrow, so the direction of the arrow is the direction of PN junction. So the arrow is pointing from grid G to the channel. So the channel is an N-channel. The electrodes on the sides near the grid. We defined it as the drain on the other side of source pole. Note field effect 2 is circuit symbol. Unlike most FET symbols, you can recognize it by its symbols. On the right is the P-channel junction FET. It makes two N-shaped regions on the left and the right sides of the P-type material. The two N-shaped regions are interconnected by electrodes from the outside. We defined it as the grid level. So the upper and the lower ends of the P-type material we defined as the drain and source. Symbols for P-channel junction FET, as shown in PowerPoint. This channel is represented by a solid line, channel to grid connection with an arrow. So the arrow is pointed in the direction of the PN junction. So this channel is made of P-type material, from P to N. So from channel. So the material on this side of the channel is the P-type material. So this is a P-channel junction FET. We take N-channel junction FET as an example. Analyze how the nodal FET works. Node FET of N-channel, its external working conditions are the grid's potential is at the lowest point. That is, the grid source voltage is less than 0. Simultaneously, leakage source voltage greater than 0. So the potential relationship of the three triodes is the grid has the lowest potential. Potential center of source, maximum drain potential. What are the benefits of this? Grid source voltage less than 0. This ensures the PN junction between the grid and the source. In reverse bias state, so the leak level potential is higher, so it also guarantees the gap between the grids. The resulting PN junction is in an inverse deflection state. If the external circuit changes the voltage value between the grid sources, of course, the grid source voltage is less than 0. So from less than 0 to less than 0 the situation changed and we found that the reverse bias between the grid and the source is enhanced. Cause the reverse bias between this grid and the source. Width of generated spatial electric field increases. This is the N-channel junction FET. Increase the absolute value of grid source voltage. That is, when the grid source voltage is more negative, then the channel gets narrower. As part of the channel, it becomes a spatial electric field zone. So only the narrow area in the middle is the N-type material, channel narrowing. That is, If the junction FET changes the grid source voltage, this makes the semiconductor between the drain sources. The wires of the channel changes. This is how the junction FET works. For instance, for N-channel junction FET, make the potential of the grid voltage more negative. Then the channel becomes narrower. This channel resistance between the drain source increases. If the absolute value of the grid source voltage continues to increase, that is, the grid potential continues to increase in the negative direction. Channels can even be completely swallowed by the spatial electric field. Then the ditch no longer exists, so the channel is clipped. Then the grid source voltage that causes the channel to break, we call it VGS off, called the clip-off voltage, as shown in the diagram. When VGS equals VGS off, full channel collapse. But it is impossible to conduct current between leaks. This is a gate voltage to N-channel junction FET, effect of channel wires. So take a look at the control of the drain voltage VDS on the channel. We say that for N-channel junction FETs, grid G has the lowest potential center of source. The potential of the drain is greater than that of the source. This ensures that it forms a reverse bias between the grid and the drain. If I will lick the potential D, the potential continues to increase. What effects does it have on N-channel? That is, if the leakage side continues to increase, what about the reverse bias between the leakage and the grid? More prominent. Then the reverse bias is increased. Then the spatial electric field will be wider. So when the VDS goes up, then the VGD absolute value gets larger. Of course, it's a negative value. A larger absolute value means a smaller VGD. Then the absolute value of VGD gets larger. This results in narrowing the channel on the side of the drain. This makes the channel resistance run larger. This is to change the drain voltage, increase drain voltage, N-channel junction FET. This channel will narrow near the drain side electrode. If I further increase the drain voltage VDS, so this channel is on the leak side electrodes, it would be possible, completely occupied by the spatial electric field area, make the channel tweezer snap. The point that is broken is called point A. This voltage VDS that cuts the channel, what we call the voltage that breaks the channel. When will the channel break? That is, when VGD is less than or equal to VGS off, the channel on this side of the leakage side electrode will be clipped. When VGD is less than or equal to VGS off, this channel will be cut on the leaky side. Continue to increase VDS at this time. Resistance between DS remains basically the same, because it was clipped. This resistance depends primarily on the length of this channel. If we do not consider the channel length modulation effect, that channel length increases with VDS. The channel has only the slight decrease. Channel resistance is only a slight decrease, so its leakage current will not change much. In this case, this breakpoint A measured voltage and the grid potential difference. Definitely, VGA is equal to VGS minus VGS off. When VDS continues to increase, then point A, the point A of the breakpoint, will move down. What is the length of this channel due to the presence of the break zone? Will get shorter. So the potential difference between point A and point G, it must be constant equal to negative VGS off. VGA is equal to VGS off. Then VAG equals negative VGS off. At such a time, point A will appear. The channel wires at point A disappears completely. So when considering the channel length modulation effect, the length of this channel, it will decrease slightly as VDS increases. If channel length modulation effect is ignored, its VDS increase. the length of this channel remains basically the same. That is, the channel resistance remains basically the same. So after pre-clipping, VDS up-drain current ID basically remains unchanged. While junction FET its volt-ampere characteristics curve include output and transfer characteristic curves. When VGS is larger than VGS off, that is, the channel is not broken, and VDS is less than VGS minus VGS off, that is, when the channel is not pre-clipped, VDS is actually smaller in this area. In this small range, ID increases with the increase of the VDS. It represents a linear resistor. Only when the channel becomes narrower, ID will increase more slowly. Presence is non-linear. The whole channel has neither interrupt due to the presence of VGS, nor is it pre-clipped because VDS exists. So this is what we call an unsaturated zone. That is, in this output characteristic curve, I use red shade to represent area. This area is characterized by the presence of ditches. No channel was clipped because of VGS, nor is the VDS too high to pre-clip the channel. In this area case, FET works like a variable resistance. When VGS is fixed, it resembles a linear resistor. When the VGS changes, inclination changes output curve. It is equivalent to a variable resistance controlled by VGS. If VDS increase to VDS greater than VGS minus VGS off. At this point, the channel is pre-clipped near the linking side. After the channel is pre-clipped, leak source voltage increase. The current ID does not increase significantly. These curves are near horizontal. That means this FET in the pre-clip state, this area we call the saturated area. Nodal FET works in the saturated region. The current ID of its output basically not affected by output VDS, only affected by VGS grid voltage. Then the grid source voltage changes, cause a change in channel wise. So this saturation can also be called an amplification zone. ID is affected by grid source voltage VGS. For an N-channel junction FET, the grid voltage must be less than 0. The lower the grid source voltage, the narrower its channel is. So when the grid source voltage is 0, it is such a saturated region with the largest output ID. Then, as the grid source voltage VGS decreases, the ID of the drain current its output decreases. Analyze based on the theory and experiment. Nodal FET, it leaks current ID. Relationship between grid source voltage and drain source voltage, as shown in the PowerPoint. ID equals approximately IDSS times 1 minus VGS off fraction. Square of brackets multiplied by 1 minus VDS, then VA brackets above. Then VA describes the channel length modulation effect, such an early voltage. VDS is between junction FET leakage sources, voltage between output port and the drain source. VGS is the voltage between grid sources. VGS off refers to N-channel junction FET. When the channel is completely clamped, that VGS value, IDSS, is a constant. It is related to the basic structure of the tube. You can see from this expression relationship between leakage current and VDS in nodal FET. It is also a relationship that satisfies the square law. However, the structure of the Morse tube is different from that of the Morse tube, so its expression is different. If I increase the absolute value of VGS, it also continues to decrease the G-point potential. To a certain extent, this will cause the channel to be completely clipped by the spatial electric field, so this channel is completely broken, what we call the cutoff zone. That is, between the leak and the source, no N-type channel is conductive, so no current ID between the drain and the source equals 0. In this case, what we call a junction FET is cut off. As shown in the diagram, when the grid source voltage VGS is less than or equal to -2, you can see that the leakage current is gone, so its condition is that VGS is smaller than VGS off. For N-channel, it is characterized by ID equal to 0. Of course, IG equals to 0. Originally, the grid is suspended, so the input grid current must be equal to 0. Breakdown zone. Look at the saturated area behind this curve. With the increase of VDS, what about ID current at saturation? It's basically unchanged, or gently slightly raised. But when the VDS is larger than a certain value, suddenly the current of the ID increases dramatically. What's the reason for this? It is because the potential of the drain is very high. Then the drain potential is high and the grid potential is low. For example, the PN junction between the grid and the drain. Possible reverse breakdown. Of course, the space electric field between the source and the leak forms such a non-conductive channel. May also break down. Anyway, after it's been hit, this results in sharp increase in the current of the ID. This is a junction FET. N-channel as an example of its 4 working areas. Let's go back and have a look. 1 is unsaturated. It's like a linear resistor. As VDS increases, because the channel is not clipped but not pre-clipped, no significant change in channel-wise. So the leakage current increases with the leakage voltage, basically a linear increase. Increase with drain voltage after pre-clipping the N-channel of junction FET, so the drain current is basically not affected by leakage source voltage VDS, so it stays flat. So what about channel length modulation? This leak current has only 1. There was a slightly gentle lift up. A working area like that is what we call a saturated area. ID in saturated region, basically influenced only by VGS and not by VDS. So it's a forward controlled. We call it an amplifier. The other 2 areas are disconnected between the grid and the source. Leaks are also disconnected from source. So what we call cutoff zones. Its condition is that VGS is smaller than VGS off. So of course its channel is broken. No more current flow. Then if the VDS is particularly old, of course, it will also reverse the PN junction between the gate and the drain. It caused an avalanche, so the ID current increased dramatically. These are 4 working areas of the nodal FET. Okay, this is the end of this class. Thank you.